is it's smooshing all of A down to a single point.
That's what you said.
Right, yeah. He says such a space is obtained by collapsing A to a point. He says, for example, we will see in the next chapter, example 4.55, the space, he says B, the closed end ball, mod the S, I can't draw his double S, n minus 1, all right, obtained by the collapsing the boundary of Bn to a point. He says that's homeomorphic to Sn. Let's see if we can think about that. I think we thought about this a little bit already, right? I think we thought about this last time, didn't we? Yeah, I think we did. So like the disk is B2, closed disk, you know, filled in. This is, I usually would call it the closed 2 disk anywhere else, but the closed 2 ball, right? And then S1, he says, collapsing the boundary. So the boundary of the closed 2 ball, right? Is S1. Right, this is the boundary, right? So if you can think about taking all of that and scrunching all the black to a point, while not, you know, scrunching the interior, maybe the best way to think about it is just kind of like, imagine pulling these points back behind the board while the middle point is stuck on the board and just kind of like pulling it back, and then you've got a bubble, right? Yeah. All right, so the next example, example 3.53, is a cone. And this is a rather general cone, all right? So if X is any topological space, what he does is well, one thing I should mention is if you take X and take the Cartesian product of X by I, what's this? This is what's called a cylinder. You know, a cylinder, I could say a cylinder over X perhaps. Do you guys see why that is? I mean, think about this. If I, for instance, if I take in the plane, right? Here's my copy of S1, right? And then I take the Cartesian product of that with the unit interval 0 to 1. What is that? It's x, y, z such that, you know, x squared plus y squared equals to 1, and 0 less than or equal to z less than or equal to 1, right? But that's exactly the cylinder, the right circular cylinder of height 1, right? Like that. So that's a cylinder. But you can do this just as well for any other shape. I can form a parabolic cylinder. I can form an elliptical cylinder. I can take any curve you like in the plane, Cartesian product with the unit interval will give you a cylinder. Yeah.
So are we going to map, like, X, or are we going to squish down X across the set 0 to a single point?
X cross 0. Is that what you said?
Yeah.
Yep. So that's the cone. Cx. So what you're doing, yeah, you can literally see it in my picture, right? You're taking the bottom circle and just to a point, right? And you're leaving the rest of them alone. So, I mean, I don't know. I guess the direct picture, it's not. I don't even know how to, but yeah, so. But yeah, I mean, if you were to try to picture it more directly without any kind of, you know, I mean, I don't even know what the direct picture would be otherwise. I mean, I think you could reasonably picture it like this too, right? Like, but this is dotted. And then there's just like one point here. Yeah. Well, there is a homeomorphism from here to here.
Yeah.
And the homeomorphism moves this single dot at the bottom to the vertex of the cone, and then it takes every circle and it just appropriately shrinks it till it's to that. And that is a one-to-one and onto bijection, which is continuous with respect to the topologies in play. Although I never defined which topologies were in play. But you can assume the Euclidean topology if I don't say otherwise. But anyway, this is the cone on X, denoted Cx. He says, it's easy to see geometrically, and we will prove it, that the cone of Sn, so he says the cone of Sn is homeomorphic to Bn. Oof. That's the open ball. I don't know if I believe it or not. Do you believe it? So like the cone of S2, I have a hard time visualizing that, though, I will admit. The cone of S2. Oof.
Well, we have the cone of S1 right there, right?
Oh, okay. Yeah, cone of S1. Let's do that.
Wait, isn't B1 just an interval?
Well, yeah, what is B1? Yeah, I think you're right. B1 should be, shouldn't it just be -1 to 1?
Yeah.
I don't see that. I don't see that. Yeah, I don't see that.
Oh, actually,
I don't see that.
Dr. Cook.
Yeah.
What if we have a spiral?
Spiral. What are you doing to me?
Imagine this. Imagine this.
That's surjective?
Imagine this.
Uh-huh.
What about the point of view?
No,
Yeah, but, well, I think your spiral idea will get in. I have trouble separating. Like, I'm thinking about like Hausdorff and how that plays with your spiral, and then I just think it's a typo. Although I'm having trouble picturing, like, what would the cone, I mean, what would the cylinder over S2 look like? I mean, I guess the cylinder over B2, right? If this is B2, right? And I'll do the closed B2 for the sake of my picture being nicer. You know, that's just a can, right? I mean, right? It's just a closed solid cylinder. I have a harder time picturing the cylinder. So like S2 is this thing, right? But empty. It's just like a basketball's surface, but not the interior. Like, what is that cross I? It's, yeah, like the Cartesian product of this with it's not.
Doesn't it go in another direction that we can't see?
Yeah, I think that's the thing, is I can't picture it directly in 3 dimensions in the same way. Exactly, 'cause since this is in 3 dimensions, I have to introduce a 4th dimension in order to.
But your picture
Yeah.
only in 2 dimensions, so it should be okay trying to.
Very good. So here, it's just this, yeah. It's just a pill.
Really do it. I'm not gonna lie.
I'm sorry, I forgot this part. But yeah, I don't know. So it's hard for me. I can't visualize the 2 case. But anyway, let me stop with that. One more thing here for today. If we have this one's very, very cool. If we have a bunch of non-empty topological spaces, x1 through xk. So I'll have to look into that. I feel like it's a typo. But then again, maybe we'll prove it, like you said. All right. So example 3.54. If we have topological spaces x1, x2, all the way out through xk. So we got k topological spaces, all right? And each one of them comes with a point, p1, p2, right? All the way out to pk. So these are, p sub I, an element of x sub I for all I, all right? So representative points, okay? Then we can form what's called the wedge sum. We can form x1, make sure I got my wedge the right way, wedge x2, wedge x3, wedge wedge xk. And what we do, and have you guys ever thought about the disjoint union?
Yeah, but only in the context of this textbook and at like 11 p.m. So I don't.
So disjoint union means.
You print out the Wikipedia page.
That's right, I did that. So the disjoint union is something you can do. For example, the disjoint union of R and R, I think is pretty much the same thing as R2. Like you're treating the set R and the set R as if they're different. So you're keeping, like if I take the disjoint union of the same set k-fold times, it's essentially just, you can identify it with the k-fold Cartesian product if you like. I mean, you can build the disjoint union formally from a Cartesian product, something like this. So disjoint union means that even if x1 and x2 have something in common, we're not identifying them, all right? So we keep them separate. So this is the disjoint union. But then, so this mod, the equivalence, which equivalence? We're collapsing the set, well, these base points, P1, P2, Pk. So what this does is it joins all of these spaces at this one common point. So, for example, if you were to take like the span of E1, wedge the span of, I meant E3, my bad. No, I meant E1, E2. And I'll use base point 0 and base point 0, right? and I'm thinking of both of these as subsets of R2, what this would be, if I call this thing, whatever. Let me just draw a picture of it. There, that's the picture of it. All right? They're joined at the origin, like that. Or we could take like circles, 2 circles, and maybe the point on the south pole of the one and the north pole of the other as our base points. This would be S1, wedge S1. So the wedge sum of 2 circles, we can get the so-called figure 8 space.
Oh, yeah. And that happens, so that's what the wedge sum does.
Mm-hmm. It's a way of building new spaces. This might be useful to us in our project as a means of like constructing examples, Come on, computer, don't die on me. This is also called the one-point union. Do you see why that is? Does that make sense?
Disjoint union, but it's not one point union.
Right. But you could, if you do this for more circles, so think about, you guys ever seen like sometimes you'll see like maybe not a keychain, I don't know what it is, but I've seen like a bunch of circles that are joined together by a ring. If you can imagine that. If I actually have that, Yeah, like that. But imagine instead that you had a bunch of keychains around the one central keychain, and then imagine the central keychain, the central ring shrinking to a point. That would give you a physical representation of like what's called a bouquet of circles. So I could draw it like this, but that wouldn't do it justice because they're not really intersecting except at that one point, right? So that's not an honest picture in some sense, They only intersect at the center point, the 1 point sum. An interesting problem is given in the handout that I gave to you guys, which is that the wedge sum of Hausdorff spaces is Hausdorff. Now, Shane, you don't know what Hausdorff is, do you?
No.
So to say a space is Hausdorff means that if you, here's my space, all right, X. To say X is Hausdorff means that if we pick X here and we pick Y here, right, given X and Y, and they're not equal, then there exists, let's say, Ux and Uy in the topology of X, right? So they're open sets, one here and one here, which, with X an element of Ux and Y an element of Uy, but Ux and Uy don't meet. In other words, a Hausdorff space is one in which you can separate points with open sets. So the claim is that if x1 through xk are Hausdorff spaces, then the wedge sum is Hausdorff. So in order to work that problem, we have to grapple with what is an open set in the quotient, right? How do we define open sets here, right? They're open if the inverse image of the set is an open set, right? In other words, the quotient map is this, that surjective quotient map is a quotient map. So you have to look at you have to define what's open here in terms of the inverse images back to, not here, but there. And the definition of the topology in the, what's the word? External, I just forgot the name of the stupid thing. Yeah, that's not it either. But that's what I wanted to say.
Disjoint.
The disjoint union, yeah, that's it. Is, something's open in the disjoint union if it's the disjoint union of open sets in the topologies of x1 through xk respective, I think that's it. But anyway, I think that might be an interesting problem to try. Exercise 355. But anyway, that's where we got to today. So sorry I didn't get further.
Thanks, Dr. Cook.